Okay, today we're going to be talking about the rigorous definition of a limit. It's also called the epsilon-delta definition, as you'll see why in just a minute. But first, let's recall our previous definition of a limit. And this is going to be our working definition. This is how we're going to be thinking about this. But let's just remember, it said that given, and I didn't write all this out, given a function f and blah, 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 that's defined on a domain, not necessarily at a blah, 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 then we say that the limit as x goes to a of f of x equals L if we can make the values of f arbitrarily close to L by taking x to be sufficiently close to a, but not equal to a. Okay? This is what we've been working with this whole time. And in pictures, what we mean by this, right, is that if you have some function, here's your x-axis, you have some function, maybe it does something like this, whatever, and you have some a here as your input. Then as x goes to a, so let's make this a bit bigger. I want to do this because we're going to do some more stuff with this. I want to do this well here. Okay, input axis, output axis, and you have some function f. And we say that the limit as x goes to a equals L, right? If as x gets closer to a, so we are imagining x getting closer to a, then the output values are getting closer to L. And we said, as we tighten up the definition a little bit, that it has to work from both sides. So as you go towards a from this side, as x gets closer to a, you're getting closer to L. Right? Nothing new here. Right? And here this is f of x right there. That's the function. Okay. Now there's two phrases in this definition that are doing a lot of work. One of them is arbitrarily close to L. What does that mean? And sufficiently close. These are what you'd call in writing weasel words. Like, oh, it's arbitrarily close. What do you mean by that? Let's be precise here. Okay, and so that's what we're going to do today. And so, like, this is more or less the definition that Newton used when he invented calculus, or discovered, depending on how you want to look at it. So, do you guys know that Leibniz, Gottfried Leibniz, you ever heard that name? No, have you've heard Isaac Newton?
Yeah.
Okay, Isaac Newton and Gottfried Leibniz. Leibniz was a German mathematician. Newton was, of course, a English polymath, and I think they were all polymaths back then, right? They did all kinds of stuff, Renaissance men, right? They, independently of each other, at the same time discovered calculus.
Oh, I think I've heard that.
If you've heard that. And so they, and everything here, I don't know about with Leibniz what definition he used, but this that we've been using is pretty much what Newton went with, right? There's this idea, just as this gets closer, that gets closer. At some point in the future, people were like, that's not really sufficient. Because when you're using functions like a polynomial or something like that, everything just kind of works out just fine. And even like exponential functions, trig functions, and stuff like that, they all have this nifty behavior that, yeah, this makes sense. But as time went on, more exotic functions were found, and more situations, scenarios came up where it was like, we need to be really clear about what we mean by this. And so that's where this definition that we're going to be talking about today came in. And I think it might have been, I know Cauchy, Augustin Cauchy, I don't know if he invented it or if like him and others, but he is like pretty much the father of analysis as we do it today. And it very well may have been Cauchy that, I don't know, came up with what we're doing today, but it was around the time of Cauchy that this definition that we're going to go into, the rigorous definition of a limit, came into being, and it turns out that with this new definition you could do amazing things, and it takes all of the ambiguity out of something like, what do you mean by arbitrarily close? What do you mean by sufficiently close? So let's start with arbitrarily close. What does that mean? And I'm going to give you an idea here. So arbitrarily close is basically within any given tolerance. What do you mean by that? Imagine that you make screws. Or that you make bolts, right? You work at a factory that makes bolts, okay? And for a given bolt, like this bolt right here, it has to conform to a certain size, right? You would like it from the top of this thread here to the bottom of this thread here. There's going to be some kind of specification for how big it has to be, okay? And let's just say that that specification is like let's say 1 centimeter. Okay, so from there to there, it has to be 1 centimeter. But in the real world, you're never going to make a bolt that is exactly 1 centimeter. You guys get that, right? It's impossible to do. Why? Well, at the scale of atoms, like are you layering these by atom? And even if you could, let's say you worked at a nanotechnology bolt factory that's making bolts as close to 1 centimeter as possible. Even if you could layer it atom by atom, even then, at different heats, it's going to expand, right? And not to mention, just even unless you're at absolute zero, these atoms are bouncing around. All atoms bounce around all the time. That's what, like, absolute zero is the absence of that bouncing around. And even then, things get weird with size and distance and stuff like that. So what I'm saying is it's impossible to have a bolt that is exactly 1 centimeter across. But if you work at this bolt factory, you're going to have a tolerance. Okay, and that's going to be some wiggle room, right? It needs to be like, say, 1.0 centimeters, but it can't be 1.1 centimeters. That's a bit too far. And maybe for the bolts that you're making, because they're very special, they're used in aircraft or something like that, they need to be even better than that right there. Your tolerance is going to be the amount of wiggle room that you have out here, right? So you have some amount that it can be. And usually a tolerance is given in the following way, in physics and engineering, plus or minus some amount. And let's say our tolerance is like out to, that's 1,000th, okay? So these bolts need to be within 1/1000th of a centimeter, otherwise we're going to throw the bolt out. Right? So you're testing your bolts as they come off the whatever, and if it's outside of this range, and let's think about what this range would be. So if you subtract off the 1,000th, you would be at 0.9939s, right? Yeah. And if you add on, you would have that right there. And as long as your bolt length, right, and let's call it that length y, as long as that, or width, I guess, is how we're talking about this. As long as that width is in that interval, you're good to go, right? So everybody get what I mean by a tolerance. There's an accepted range in which you could have something, okay? Now, if a limit exists, then what this means, so this arbitrarily close here, is what we're saying is that if this limit exists, then this tolerance can be made arbitrarily small. Okay, so hang on to that idea for a second. So here, you can't make this, in the real world, you can't make this arbitrarily small, because eventually, if you add on enough zeros here, you get smaller than the Planck length, and past that, there's no way to measure that. It's like the idea of distance doesn't work. You can't make anything arbitrarily small, but if a limit exists, then you can make the tolerance arbitrary. And you keep saying, well, what do you mean tolerance here? I'm not seeing a bolt. We're going to get there in just a second, right? But what we're saying here, arbitrarily close, means that we could get within any desired, like if however many zeros, 0.1. What about this right here, 2718? Can we get within that close? Yes, you give me any desired tolerance, and I'll be able to dial in F arbitrarily close to L. Okay? Following me here?
Yeah.
Okay? Now, when we're talking about an arbitrarily small number in mathematics, we usually use the Greek letter epsilon. Okay, that's epsilon. It's spelled epsilon. We say epsilon like Greeks would say epsilon or whatever, but like we call it epsilon. And so we're talking about a positive number. You're going to see, if you go into analysis, you're going to see this all the time. Epsilon bigger than 0. And that, but anytime you see epsilon, we know that we're talking about a very, 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 very small quantity. And I'll probably, now that I've said this, I'll probably use this throughout the year at some point. Say, okay, just give me a tiny distance, and I'll call it epsilon. Or give me a tiny amount. Okay, epsilon, right? And we understand it's some positive number, but it's really, really, really small. Okay? So this is kind of like your epsilon right here. That tolerance, like you have some distance that you're shooting for, but you know you're never going to get that exact distance or that exact length or whatever. And so there's some kind of error, right? And that's another, you could think about that E as being for error as well, right? And as long as you're within there, you're good, blah, 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 blah. Everybody tracking me so far? Okay, so back to this limit here. This statement right here, another way of saying this, is that if you give me any tolerance, right, any plus or minus some amount, if you give me any tolerance, no matter how small, and we'll say epsilon, some tolerance, tolerance bigger than 0, some epsilon. Okay, so in other words, we're thinking, okay, we want to, because remember the whole point here is we're making values of f, output values of f, arbitrarily close to here. And so let's do this. We're going to call epsilon, we're going to do it in red. Okay, you've given me that. Okay, and maybe it's like a billionth, maybe it's a billionth of a billionth. Maybe it's a trillionth of a billionth of a billionth, right? It's a really, really, really tiny number. And so we go some distance away from L epsilon. There's my tolerance, right? We could bounce back and forth between there. You give me any tolerance, and we're imagining it's really, really, really tiny, right? Quick question. If this is L, and we go up by epsilon, then what number would this be right there?
L plus epsilon.
Yeah, L plus epsilon. Good, okay. L plus epsilon right there. If that's L and we go down by epsilon, what number is that?
L minus.
L minus epsilon right there. Okay, and L is this big guy right here. Okay, and there's L minus epsilon. Okay, so get ready, because here it is. This is the big idea. This right here, this statement, the limit as x goes to a of f of x equals L, means if you give me any tolerance, no matter how small, boom, then I can find a range around A. I could find another number, and I'll put it this way. I can find, I want to see how did I put this. No, I did want to say this first, okay? So it means that if you give me any one of those, any tolerance around L, then I can guarantee that if you get close enough, if you get sufficiently close to A, then the output is going to be within that tolerance. You see what I'm saying? That if you give me an x sufficiently close, and now we're going to have to figure out what that means. if x is sufficiently close to a, then I can guarantee that the output f of x will be within that tolerance. Now, what do we mean by sufficiently close? Well, that means, again, if you give me any tolerance, no matter how small, around L, you give me any tolerance, then I can find another parameter called delta, which is also bigger than 0. And that is just another distance, delta. This, by the way, is the Greek letter delta. And if you're within delta units of A,
Delta was a triangle.
capital delta is that. Lowercase delta is that. Good. Yep. So, and in Greek it would be delta, by the way. So anyway. Okay, then I could find another tolerance, basically. I could specify that. If you're within here, then all of the output values, now you see I didn't do that very right. I didn't do that right. Delta would have to be even smaller, wouldn't it? Okay, so then I could find a delta so that whenever you're within there, okay, then you will be within epsilon of L. Does that make sense? So I could find a delta so that if x is within delta units of A, then F, which I did in black, will be within epsilon units within your tolerance of L. Does that make sense? Any questions about this before I go on? Because this is the just regular parlance of saying it, and what I'm about to do is erase this and put the formal definition. Like, we're going to translate this into math speak. But does this make sense? Yeah. And it kind of makes sense visually, right? It's like, well, I want my outputs of this function to be within, say, 1/100th of L. So that would be L plus 100th, L minus 100th. Or if you think back to this, let's say that L is 1 centimeter. And that my epsilon, so if my L is 1 centimeter, and my epsilon was, what did I use, 0.001 centimeters? Then my L plus epsilon would be my 1.001. My L minus epsilon would be 0.999. And what we're saying here is that I can make the values of f of x, within this range by taking x to be within a certain distance of that target right there. Okay? But not equal to the target. Right? Okay. Okay. So, here we go. So here's the formal definition. I'm going to get rid of all of this. And yeah, I am going to do the full shebang, aren't I? So here's the big idea here. And in just a minute, we're going to do a few examples, and you're going to see why you're never going to see this again. Because this makes your life, forgive me for saying this, a living hell. It gets so bad. But here we go. Okay, ready? Let f be defined on an open interval? Remember, open intervals are something like this, right here. Right? It's open. You're not closed. It's not, you know, you're not including the endpoints, whatever. And it could be on all real numbers. Like any polynomial is defined on all real numbers. That's an open interval. We don't include infinities, right? Okay, let f be defined on an open interval that contains a. And that's kind of what I've done here, right? I haven't been very specific about what happens out here and here, but we could say at the very least, it's defined from here to here. You've drawn that, meaning it's been defined. And yes, a is in that interval. Okay, so there's your picture to go with that statement. Then we say, the limit of f of x as x approaches a is L, and write lim x goes to a, f equals L. So this is the setup that I didn't write before, right? That's all the preamble and blah, 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 blah. And then we write this. And that means we write that if for every number epsilon, that's positive, every positive number or every tolerance, no matter how small, every single one, if this is true. If for every number epsilon there is a number delta, also positive, so you give me a tolerance, I could find another distance right here, right? There is a delta such that, and here we go, such that if something then something, such that. So all of this, right, okay, we say that this limit exists. In other words, we say that this limit exists if you give me any tolerance, and I could find one of these, so that what? Well, we're going to translate all of this into math speak now, and this is how you do it. That if the distance from x to a is less than delta, then the distance from f to L is less than epsilon. That is the rigorous definition of a limit. Now let's pull some of this apart here. Okay. First off, let's look at this part right here. 0 is now you understand that this is the distance from between x and a, right? Like, and the reason why it's absolute value is because it works on both sides, right? If I took x minus a, since x is on the left-hand side of a, that would be a negative number. But we don't care if it's negative or positive, so we take the absolute value of it, right?
Yeah.
Right? So that's what the absolute value is there for. And what I want to do here is tease out like what this means. So that first part, that this being bigger than that, all this means is that x can't be equal to a, right? Because the only way that that's not true, right? This will always be true. The only way it's not is if x is equal to a. But when x is not equal to a, that's always true. Give me any two numbers that aren't equal, 5 and 2. Subtract them from each other. Take the absolute value. Is that bigger than 0? Yeah, the only way it can be. So all that whole left-hand part there, and in fact, in many books, you won't even see that part because it's really not. This is more. We're kind of getting in the weeds here. This is like at the end we tacked on, but not equal to a. And so yeah. As long as it's not equal to a. In other words, that there is just pulling that weight right there. So that way we don't have to at the end append and say, but x can't be equal to a. That takes care of it. Everybody got that? Yeah. Okay. Now, let's look at this part right here. That part. x minus a. In other words, the distance from x to a is less than delta. Now, does anybody remember how you deal with something like this if you have some function in here with an x in it, like, I don't know, x plus 2, and you have something like this? How do we get rid of those absolute value bars?
It's like the plus or minus on either side of it.
Yeah. Well, you mean this right here?
Yeah.
Right? Because that's what that means, right? Everybody got that? Right?
Yeah.
If the absolute value of x is less than 3, then that means that x is bounded below by negative 3, and it's bounded above by positive 3, right? Okay, so that's algebra 2 stuff. And why did we ever cover that? Because of this. This is why we talked about that at all, right? Is now, okay, what does this mean? So let's drop those absolute value bars by doing my positive delta here, my negative delta here. And now I get that right there. Why don't we add a to both sides, and we get a minus delta x, a plus delta. And we didn't do this. If that's a, and this distance is delta, when you go a plus delta, and I did this terribly, I didn't draw. If I would have thought this out, I could have done this better. And actually, it's kind of good that I did this, because you can't, if you're out here, you can't guarantee, well, I mean, you just whatever, I'm not even going to say it. A plus delta, a minus delta. The same way we did right there, right? You're at a, you go some distance delta, you're at a plus delta. You're at a, you go that way, a distance of delta, you're at a minus delta. So as long, whenever this is true, then you could guarantee this, which is f of x minus L less than epsilon, which, write this without absolute value.
Negative epsilon is less than f of x minus L, which is less than positive epsilon.
And what happens if I add L?
L
L
minus
plus.
epsilon is less than f of x, which is less than epsilon.
So that's what that means. That's what we've been talking about this whole time. You give me any epsilon. If the limit exists, then you could give me any epsilon, and I can find a delta, which will have this property, that whenever x is within delta of a, so it's within this bound here, I'm somewhere in between a minus delta and a plus delta, then I can guarantee that my outputs, f, will be within this interval, L plus epsilon down to L minus epsilon. Another way of writing this is to say that whenever x is in a minus delta, a plus delta, then f of that very x will be within L minus epsilon up to L plus epsilon. It means the exact same thing. In fact, I could have defined it that way right here, and we have exactly the same thing. But this is how you will see it. And very often when you see it, they won't even bother with that right there. But anyway. So, does this make sense to everybody?
Yeah. Yes.
Okay, here's what I want you to... This might show up on a quiz. If I ask you, what is the rigorous definition of a limit, this is what I'm looking for. I'm going to get rid of this, because I'm not looking for all that. I don't care about if it's defined on an open interval. We're not taking analysis, so we don't need to worry about that. This is what I'm looking for. If I say, what's the rigorous definition of a limit? This is what I'm looking for. That the limit as x goes to a of f of x equals L means for all epsilon bigger than 0, there exists a delta also bigger than 0, such that if you commit this to memory, your life will be much easier in the future. This is for all epsilon. Then whenever you see that, you can think of, you give me any epsilon, any positive number. It could be a billion, it could be a billionth, it could be 7 trillion, it could be 1/7 trillionth. Doesn't matter. Any tolerance, any tolerance around L, then there exists. I can find a delta, which is also positive. I can find another distance so that whenever you're within that distance of delta, whenever you're within a delta distance of A, right? That's what that means. Whenever you're within a delta distance of A, then I guarantee that F will be within epsilon distance of L. Everybody got that?
Yeah.
And this is a really succinct way of writing it. Okay, so this, if and only if, for all epsilon bigger than 0, there exists a delta such that this implies this. Another way you'll see it written, and this is nice, this kind of goes along with the way that you actually do one of these proofs. You could do it this way, you could think about it this way, that this means that for all epsilon bigger than 0, there exists a delta bigger than 0 such that this is true whenever this is true. It means the same thing, right? If this, then this is the same thing as saying this whenever this, right? If A, then B means the same thing as B is true whenever A is true, right? So this is, but that's not what I'm looking for. You could do that, that's fine. And in fact, I think that's when I learned my first class on analysis, that's what they put up on the board, right? But this is, remember, this thing means if this, then this, right? So A implies B means if A is true, then B is true. Okay? Questions?
I don't think so.
Okay, before we move on, we're gonna go. So everybody got this right here? Because I guarantee you're gonna see it on a quiz. I guarantee. I'm just gonna say, give me the rigorous definition of a limit. That's what I'm looking for. And you just didn't know what this means. For all. That means for all. This means there exists. And this bit right here, when you're dealing with like, I want to prove that a limit exists, really what you're trying to do is you're trying to show what delta is. You give me any epsilon, we're going to write epsilon, and we're going to pretend that's a really small number. Can I do some magic here to show that there is indeed a delta, which makes that true? We'll do that in a minute, and you'll see what I mean. But really, that's the key right there. You give me any tolerance, can I show that there is another corresponding tolerance so that when I get my inputs close enough to that, within that of that, then we get the blah, 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 blah. Everybody got it?
Yep.
Can I erase it?
Yes.
Okay, you're never going to see it again. But you'll see it on a quiz. Okay, so here we go. One quick thing that we have to do is a triangle inequality. A plus B, the absolute value of A plus B, is less than or equal to the absolute value of A plus the absolute value of B. Does that make sense? Think about it this way.
Oh.
These are just two numbers, and they're either positive or negative, right? So, like, you might have like a 5 plus a negative 2, right? And all this says is that if you take the absolute value of that, that has to be less than or equal to the absolute value of each of them. Right?
Well, wouldn't it always be equal to that? Wait.
Is this equal?
Oh wait, no, it's not.
Yeah, see, that's why it's equal when they're both positive. If they're both positive, then you've taken absolute values of positive numbers and everybody's happy. Well, let's see. Absolute value of 3, that's just a 5. That's just a 2. That's a 7. Is the absolute value of 3 less than 7? Yeah, right. Now, if it were positive, positive, then they'd end up being equal, right? Because you'd have plus 5 plus 2 is indeed 7. And so, yes, then equality would hold, right? Okay, so everybody buy that? We're not going to prove that. As far as I'm concerned, I just proved it. Like, it's called the triangle inequality. We could talk about why about today. But, okay, so Now we're going to use the rigorous definition of a limit to prove one of the limit laws that we talked about, okay? And I was going to do this. I was looking forever last night, like an hour I spent doing different things like for a good example. And everything turned out to be ridiculously complicated. I was like, okay, you know what I'm going to do? I'm going to do something like this. X minus 1 over x squared minus 1, the limit as x goes to 1, which we know is what? Let's simplify this.
It's just
X minus 1 over x plus 1.
Yeah, x minus 1 over x plus 1, x minus 1.
Yeah, you can't.
And so those cancel, so this is the same as that. And so this limit is what?
0. Wait.
As x goes to 1.
Oh, it's negative 1.
It's 1/2.
1/2. Right, we just plug it in.
Yeah.
Right? So that's what we did last time. And what I was going to do is use the rigorous definition to prove this. Oh my, it is ridiculously hard. And it was really hard. And then you have to like make some arguments that are kind of convincing and stuff. If you're interested, your book in this section, this is 2.4, I believe. Your book has some great examples, and as you can see, ridiculously hard. So all through section 2.4, like you could do it. You could use the rigorous definition to prove all this stuff, if you're so inclined. So the one thing that I was like, okay, you know what? Screw it. We're just going to do this one limit law, and it's the one that's actually in the book. And so I have not looked at the way the book does it. I'm pretty sure we do it the same way because this one's very straightforward. But again, like, you're going to see why we don't do that, why this is not going to really help us. So with that limit law, remember the very beginning of the limit laws, we had to suppose as I like to do, suppose that the limit as x goes to a of f of x is equal to L. And suppose that the limit as x goes to a of another function g is equal to m. And of course it's the same preamble that they're defined on an open interval, blah, 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 blah. And what we want to show is that the limit as x goes to a of f of x plus g of x is equal to what? Limit law. What does the limit law tell us?
F of x. Well, the limit as x goes to a of f of x plus the limit as x goes to a of g of x.
Right. So you take the limit of that one, and the limit of that one, which in short would be L plus M. Right. I'm jumping to the chase here, but yes, the limit law tells us that you take that guy. It's the same thing as doing the limit of the f plus the limit of the g. And it tells us that the limit is L, that limit is G, and so it's just L plus M.
Yeah.
Yeah? Okay. Okay. That's what we want to prove. To do what we're going to use the rigorous definition. So let's unpack this. And I'm going to write the rigorous definition of this guy right here. The rigorous definition says that for all epsilon bigger than 0. Now, since we're doing a bunch of limits, right, I'm going to have one here, and then I'm going to have another limit here. That's like 3 limits. I don't want the same epsilon. So I'm just going to number it. I'm going to call this, for all epsilon 1, you give me a new variable. I would say, you give me your first tolerance, and you say 0.0001. Okay, that's what we're saying right now. We're just labeling it as a specific one. You give me, you fill in this blank with anything you want. This one is going to have a different one. And we're going to call it epsilon 2. And so you could fill in the blank with any number you want right there. And then this one that we're going to work on is going to have another one, and we're just going to call him plain old epsilon. But again, that could be any number you want, but now we've named them, right? That's all we're doing here. Everybody got that?
Yep.
Okay. So this means that you give me any epsilon 1, then there exists a delta 1, matching them up, right, so we don't get confused, such that whenever you put x within delta 1 of a, then F will be within epsilon 1 of L. This means that for all epsilon 2's, there exists a delta 2 bigger than 0, such that whenever you are within delta 2 of A, then G is within epsilon 2 of N. Yeah?
Yeah.
Now, this is the one that we're trying to prove. So what do we need to show? Well, first off, we need to say, give me a tolerance. Any tolerance. Let's call it epsilon. We need to show that for all epsilons bigger than 0, there exists a delta. That's what we need to show right here. That we need to find what that delta is, such that whenever x is within delta of that guy, we get, that this function, which happens to be f of x plus g of x minus that L plus M is less than epsilon. That's what we need to show right there. How are we doing? Okay, we have 10 minutes, 15 minutes. Okay, so that's what we need to show. Here's my proof. And this is how epsilon delta proofs always start. Let epsilon be given. So in other words, now you specified this. You're like, I don't think you could get within 1,000th of that. And I say, oh yeah? Well, let me show you. And so I take whatever that is. I take my 1,000th. So now you've given me that epsilon, and what I'm going to do is say, let me tell you how close you need to get. Because that's what I'm trying to do now. I'm trying to show how close do I need to get your outputs within 1/1000th of L plus M. Okay? Everybody get that? Okay. So this is, and now what you usually do is you monkey around with this until you could find something. And this is what you would do. You would say, all right, let me just, and this probably wouldn't be in my proof write-up, but although very often this is how it does show up. And you go, okay, let's monkey around with this thing. This is the same as f of x minus L plus g of x minus L. Did I get that right? Right? I distributed the minus over so that this thing is the same as f plus g minus L minus m. And then I just switched the L and the g. Why did I do that? Well, because now look at this, right? That looks very much like that right there. This looks very much like that right there, which, since the limits exist, I could guarantee that there exist deltas which get me to however close I want. And so now I notice triangle inequality, f of x minus L, g of x minus m. I need to show that this is somehow less than epsilon. That's what I'm trying to do. This is my goal, and I'm asking myself, can I show that? And one thing we could do is say, well, hold up. This works for every epsilon 1. And here's a cool little trick that you'll see. You go, well, since this is true, then given epsilon over 2, here's this now, I'm saying, given this tolerance, why epsilon over 2? Well, if I could get this to be less than epsilon over 2, and this to be less than epsilon over 2,
Oh, yeah.
then I'll have it let the epsilon over 2 plus epsilon over 2 will be that. So like when you read this, you're like, where did this come from? It's because whoever wrote this has done this 1,000 times. And this is one of the tricks you do. You take an absolute value and you break it into however many things. And that thing needs to be less than some number. and you have that many things, in this case 2 of them, so you could say, you know what, if I could get this to be less than this right here, plus that right there, then I'll have the thing that I want. If I had 3 of them, I would say epsilon over 3, epsilon over 3, and then I'd add in another plus epsilon over 3, right? So that's the idea. Peter, please keep it down, buddy. I need you to keep it down, please. Okay, so since this is true, now I'm going to give this one a tolerance. I'm going to say, given this tolerance, then there exists a delta 1 positive so that f of x minus L is indeed less than epsilon over 2 whenever x minus a is less than that delta 1, whatever it happens to be. And it's different for different functions, right? Like if f of x, let's say f of x is just x plus 1. That would be a really easy one. And let's say that a was like 2. And you could say, that output would be 3. And I could say, how could I get within 1,000th of that? Well, this is actually pretty easy, because you could just say, well, 1,000th here would bring you down to 1,000th here, because there's no stretching factor, right? 1,000th here would bring you within 1,000th here. And so I could say 2 plus or minus 1,000, right? You'd be between 1.999, right? And I could find it. Now in this case, I don't actually need an explicit one. I could just say, because this limit exists, whatever it happens to be, there is a delta which does that job. Everybody got me on that? This is why, and this is where your brain starts breaking, because the more complicated these get, the crazier this gets, and you're like, where did this come from? Where are you pulling it out of? This is why we're never going to do this, okay? And also, since, on the other hand, since this is true, since the limit also exists at a, then, given another epsilon over 2, which is now playing the role of this guy, for all of them, any one of them, is that a positive number? Yeah, because I said let epsilon bigger than 0 be given, divided by 2, still positive. Okay, then every positive number, there's a corresponding positive number, we'll call it delta 2, so that g of x minus m is less than epsilon over 2 whenever 0 is less than the distance. So whenever you're within delta 2 of that distance. So now we have 2 numbers. They've popped out of nowhere. Well, they popped out of this right here. We say that yes, these things exist. And like I showed you here, we could, if we had an actual functions, we could actually find what those tolerances would have to be. And so what we're going to do is this. We're going to say, okay then, let delta equal the minimum, the min of either delta 1 or delta 2. Yeah? So like one of them's 1,000th, but the other one is 1,000,000th. Well, you just take the smaller of them. And yeah, and then both of those conditions will hold. If that's less than 1,000th, okay, that's less than 1,000,000th. Well, you just specify that this one being less than 1,000,000th, and you get this one for free, basically. Everybody get that? So let delta be the minimum of those 2 things. Then, if 0 is less than x minus a less than the minimum of those, then both of these are true. Then both of those are true. So, if this, then f of x minus L plus g of x minus m will be less than epsilon over 2 plus epsilon over 2, which is epsilon, which is what we wanted to show. You gave me an epsilon. So, in summary, given epsilon bigger than 0, there is indeed a delta, so that if my x less than that delta, then, and I'm going to do the whole thing here, then f of x plus g of x minus L plus m, which is less than this guy, f of x minus L plus g of x minus m, is less than epsilon over 2 plus epsilon over 2, which is epsilon, which is what we wanted to show. So therefore, this limit does indeed exist. You see why we're not going to do this? Yeah, right? But we do need it to prove these limit laws. But once you have the limit laws, good to go, right? We're home free, okay? Okay. Now, Appendix F in the back of your book has all of the other limit laws proven in the similar manner. You can take a look at the product one. It's ridiculous. It's so ridiculous. I was gonna do the product one, and then I was like, we don't have time for that. It is hard. Okay, now we're gonna go down and dirty here. I'm just gonna put a bunch of stuff on the board. So, definition. Here's another one, and I don't think this is in your book. The limit as x goes to infinity of f of x equals L means. See, we haven't done this, and I don't see it in your book. So, but anyway, we've seen this, right? This is how we defined E, which you could define as going to 0, but we did it with going to infinity, right? And so what does that mean? Well, it means for all tolerances bigger than 0, there exists an n also bigger than 0, such that if x is beyond n, then you're within your given tolerance. So for instance, f of x equals 1 plus 1 over x. Looks something like this. There's an asymptote at 1. My claim is that the limit as x goes to infinity of this thing is equal to 1. What does that mean? Well, you give me any tolerance, right? You give me any tolerance around 1. And let's say that that tolerance is like 1,000. Then I can find an x, or rather I could find an n, so that whenever x is beyond n, right? Whenever x is past that n, then your function is within that tolerance. Does that make sense?
Yes.
And we could actually do this here if we were so inclined, and I'll bet you it would be like 1,000, right? Right? Oh. Plug in 1,000 and you're within there, right? Yeah. So then whenever, so n, in fact, can I find it? Yes, I can find it. Whenever x is beyond 1,000, then this will be true. Yeah, okay, good, found it, proved, nice, okay. I mean, we could go through and do the actual algebra, but that makes sense, right? So it's a very similar thing, only instead of there being another distance, you're just saying, once you go past this value, you're good to go. Okay. So here's an example. The limit as x goes, actually, yeah, we don't need to do that, we're running out of time. It's basically the same thing. I just, instead of having that, I did something else. And it's good. Okay. Couple more. Now this one is in your book. Definition. Limit as x goes to a of f of x equals infinity means for all m bigger than 0, there exists a delta bigger than 0 such that if x is within delta of a, then f of x is bigger than m. So think about what a function that at a, the limit's infinity. Well, a is going to have, we already talked about this, a is an asymptote by definition. And so it does something like this. And it goes the same way from both sides. Okay, what does that mean? Well, you give me any m bigger than 0. Let's say m is a billion trillion. Then what I could do is find a delta. I can find a delta so that, there's my delta right there. So that whenever you're between there and there, then the function itself is bigger than m. That's what that means. Right? Okay. So we're going to do a quick one. Using this definition, we want to prove that the limit as x goes to 2 of 1 over x minus 2 quantity squared is equal to infinity. Okay. So we need to show that it's because this means that for all m's we could find a delta to make this true. So when you get close enough to a, in this case a is 2, when you get close enough to 2, then your thing will be bigger than your tolerance. In this case it's not a tolerance, it would be a bound. And so in other words, this becomes unbounded, right? F of x bigger than whatever bound. And ditto with negative infinity. It would just be that f of x would be less than m. Now you're looking at something like this, and your m is down here, and what you're saying is that f goes below it. Okay, so who cares? Okay, so what we need to do is say, okay, prove this. Okay, here's my proof. Let your big old number m be given. Now I'm going to monkey around with this until I could find a delta. And this is how you would do one of these. You would say, okay, f of x bigger than m. Can I get that? Okay, well, f of x is this, 1 over x minus 2 squared. Can I show that that's bigger than m? Can I find an x that makes that true? Well, let's see, how about this? It's not that I'm trying to find an x, I'm trying to find this guy right here. And in this case, that would be an x minus 2. I need to find a delta to make this true, right here. Well, let's see what happens. I'm going to do a switcheroo, bring my m down here, and bring this guy over here. I'm going to note that if I'm squaring something, it's the same thing as squaring its absolute value. Ooh, nifty trick. Right? Yeah, and now I could take a square root of both sides. Knowing that I'm taking the square root of something positive, this is positive, right? So I don't need to monkey around with that plus or minus stuff. Nifty little trick, huh? So I'm going to take the square root of both sides, and what I get is that 1 over the square root of m. Okay, right there. And now, oh, that's my delta. Okay, and so now that I've done that work, I'm going to actually do the proof. Okay, so let m bigger than 0 be given. Okay, then take delta equal to 1 over the square root of m. Then, if x minus a is less than 1 over the square root of m, squaring both sides gives us, I don't care about this side really. Again, like when you do analysis, you never even touch it. But this is true. Yeah? And I'm just noting that, well, it doesn't matter if it's absolute value. Once you square it, it doesn't matter. X minus a squared is this, that's the same thing. Those are both true. If that's true, then that's true. And now I could say that m, which is what we wanted to show. We showed that the function gets bigger than that. I found a delta, right? You gave me a m. I explicitly found a delta, which makes this true. Or rather, you gave me an m. I found a delta, which is a positive number, such that whenever this is true, see, that was less than delta. Yep, that was less than delta. And look, I stopped. I did a. I just made it 2. I'm sorry. This should have been a 2. Right? So that whenever that was true, okay, we're assuming this is true, then this is true. If this, then this. I got it. Nice. And that's how epsilon delta proofs work. You monkey around with the epsilon, and I'm sorry, there's no epsilon here, but these are also called epsilon delta definition. And when you do work with an epsilon delta definition, it's called an epsilon delta proof. So that's how they work. You start with your epsilon part and go, oh, ooh, nice, that looks like my delta part. So then you come back and say, okay, now I found a suitable delta. And whenever delta is that, then that, and that fulfills that right there. You could see why we are not going to do that this year. And really, it's becomes very important later on and stuff. But again, right now we want to count with our fingers, right? Because we want to get a feel for what this stuff is, what it means. We're only 3 minutes over, so let me just real quick. I said if there's time, I'm going to put these up on board. There's also left and right definitions. So the limit as x goes to a from the left of f means that for all epsilon bigger than 0, there exists a delta also bigger than 0, such that, but now we only care about one side. So here's my a. We only care about getting close to a this way. And so x is somewhere in here, and we want to go up to a and down to, well, a minus delta. All right, so you're still within delta of a, but you're only on one side of it. So what this is saying is that you're between a minus delta, x less than a implies that f of x minus L is less than epsilon. So that whenever you're on the left-hand side of this guy, and so what that would look like here is you have an a, you have some function that does this, and so here's your L, there's your epsilon. Epsilon, that would be L minus epsilon, that would be L plus epsilon. I could guarantee that you'll be within there as long as you're within here. Right, so that's the left-hand side. The right-hand side is the same thing, only it's the limit as x goes to a from the right of f equals L. Means that for all epsilon positive, there exists a delta positive such that now you're on the right-hand side. When you're on the right-hand side, then your f is within epsilon of your target L. And that's all I got today. So this is why we're not doing these. It is ridiculous. They're ridiculously hard. And really, it's not going to help you with everything else that we're doing this year. Like there's not, like really, in the rest of this book, there's nothing that this is that using this method is going to help you with. So we're not concerned with it. So